Thank you. Let's do a quick test here. Good, okay. So I'm gonna have to really move close to this thing. So, hello friends, how's everyone doing? All right? Cool, cool, cool. So in this presentation, we're going to look at graph databases. But before we explore them, we'll consider the importance of graphs, the underlying data structure that powers GraphDBs. Undoubtedly, you're familiar with graphs, those charts showing colored bars, pie slices, and points along a line. However, those are not the types of graphs we'll consider. The graphs we're interested in consist of circles and lines and are commonly known as network graphs. Here's the same graph defined in scientific terms, that is, mathematics and computer science. A thing is represented by a vertex, and a link is referred to as an edge. We can think of vertices as representing nodes and the edges as the relationships between them. From here on out, we'll simply refer to these as nodes and links. Graphs can take on real-world meaning, such as revealing the relationships between people. For example, in this graph, Tom knows Alex, but doesn't directly know Bill, or even his neighbors, Susan and Jane. If Tom wanted to meet Susan, he could ask Alex to introduce them. When lots of nodes and links exist, graphs can become quite complex, such as with the web of social and business relationships found on Facebook and LinkedIn. Graph diagrams made their debut in a paper written by Leonard Euler. In 1735, from his home in St. Petersburg, Euler turned his attention to a problem debated by the people of the nearby town of Königsberg. The townspeople pondered whether it was possible to cross their town's 7 bridges without crossing one twice. In his short paper, entitled The Solution of a Problem Relating to the Geometry of Position, Euler represented landmasses as nodes and used links to represent bridges. Euler offered a proof that such a path could not exist, meaning that with the 7 bridges, you could not actually cross one only once. It wasn't until later they built an extra bridge that it was possible. Hundreds of years later, researchers are using graphs to explore topics such as biodiversity, terrorist networks, and the global spread of epidemics. Here's a graph that links 40 of the earliest known AIDS patients by sexual contact. On a lighter note, you may have recently taken a train ride. Did you enjoy writing a graph? If you consider a map of the New York City subway system, or any subway in the world for that matter, and if you label the train stations as nodes and the routes connecting stations as links, you'll quickly see a graph emerge. Nodes are sometimes referred to as hubs when one or more path or link converges. The New York City subway system has hubs at 34th and 42nd Street, which allow one to switch trains and travel other parts of the subway's network graph. Consider 3D games. The characters and terrains are built from wireframe models called meshes, which are essentially graphs. Ever wonder how computer game characters find their way within a game world? Dijkstra's algorithm employed in computer game AI uses a weighted graph to find routes. Turning our attention to nature, close examination of leaves reveal a network of passages which deliver water and nutrients to vibrant leafy greens. If you recall your high school biology class, then this image might seem similar to textbook diagrams illustrating our own nervous system and arteries. In truth, we need reflect no further than our own thoughts to realize that the neurons in our brains form a network graph. Indeed, graphs are everywhere. Not only do our own bodies consist of graphs, it turns out that graphs are fundamental to how we actually think. Since infancy, we catalog objects and assign properties to them. We then map objects to one another based on relationships. This process continues well into our adult lives as our minds organize information by creating the mental graphs we call memories. This all brings us to graph databases, software tools for building and working with graphs. Rather than organize data as collections of tables, rows, and columns, or even as collections of documents, graph databases allow us to model data and relationships in ways that closely mirror how we naturally think about them. Let's take a closer look. In this graph, we have nodes and links that have associated properties. Hence, this type of graph is often referred to as a property graph. We have age and interest properties associated with each person, and we could have easily added other personal characteristics. In the relationship link, we've stored information about when a relationship began. Such a graph could become the basis for an intelligent contact management application. During the past decade, we've seen an increase of interest in the graph database space. As a result, there are now many graph databases to choose from. We're going to use the world's most popular graph database, Neo4j, affectionately referred to by fans as Neo. Getting started with Neo is easier than with most database products. You can try Neo without installing it by simply provisioning a free instance using the Neo4j sandbox. Or you can download a free copy for your laptop. However, being a big fan of Docker, I prefer to download and run Neo4j from a Docker container, so that's what I have here on my machine. Neo4j comes with a web-based dashboard that allows you to interact with Neo. It's a great way to learn about Neo and later create and test your own data models. Here we see a dashboard view which allows us to enter queries and graphically see the results. Looking closely at this slide, you can see some of the concepts we've encountered in this talk. Neo4j has a declarative query language called Cypher. You can see it there at the top in the editor. Cypher queries consist of statements that use patterns to specify paths within a graph. In Cypher syntax, a node is represented inside of parentheses, and links are referred to by lines and square brackets. Node and link properties are specified using curly braces. So in addition to queries being declarative, they're also visually descriptive. Let's take a closer look. We can locate a graph node representing Alex with this query. There are a few important characteristics in the query shown. On the first line, we see that we're trying to match a node represented by a query enclosed in parentheses. The p-person fragment says, map a variable called p with a label of person. So here we learn that nodes can have labels, person, and that we can assign them to variables p. On line 2, we simply return the contents of p. We can enhance our queries by specifying the use of properties and values and listing them within curly braces. So name Alex says we're interested in only matching nodes which have a name property containing the value of Alex. If we wanted to return all of the people in our graph, our query would be even simpler. Let's try this in Neo4j. Actually, the example you see is from the repository associated with this repo. You can pull this and play with it. So here we see that the query, returns the node P. We can see that here. You can also see from the interface that it's calling this a person. And there's Alex, and if we scroll down, you can see, this is really zoomed in, probably doesn't need to be zoomed in that much. You can see at the bottom that as we hover over Alex, we see that there are properties associated. The node ID, Alex is interested in parties, his name is Alex, and has an age of 34. So bringing back that query, if we remove the specificity of Alex, we can see that we actually get back all the nodes in the sample graph because we didn't specify an individual. Also, if you're not familiar with Neo, you can see you can interact with the graph. You can click on links and nodes and actually see their properties. So Alex is connected to Susan by a relationship link with a label of nodes. That link also has a property called since. We could write a query that includes a relationship by using square brackets. Notice that we assign the variable r to the relationship link. We also use the label nodes to specify the type of link we're interested in. The label could have been something else, such as worked with or hired by. Let's say that Alex is planning a party and would like to invite his closest acquaintances. Here we omit the query for the person's name property so we can match any person that Alex directly knows. Now let's say that Alex is at a bar and is feeling pretty good, perhaps better than usual. He yells out to the bartender, "The next round is on me." Here we omit the knows relationship because it's unlikely that Alex knows everyone in the bar. Let's consider another example. Susan is planning to open her first dance studio and needs business advice. She doesn't directly know a person with an interest in business, but her dad Bill does. Here's one way to write the query. The new bit is the syntax r knows *2. This is referred to as a variable length relationship. Here we're saying, match a person node with a property named Susan, with a path of one or two knows relationships, friend of a friend, to a person with an interest in business. So we see the connection there. Now, if Jane were looking for a chess player, we'd have to specify node *3 or more for 3 hops to get to Tom following the green path shown. Now, you can also see that there is a red path leading from Jane to Tom, which involves 4 hops. Neo4j returns the shorter of the 2 paths. The ability to traverse a network of relationships is one of the great strengths of graph databases. You can ask questions such as, find a friend of a friend or more who matches a particular criteria. This is also where relational database systems and their use of joins become far less than ideal at scale. Such queries are also how recommendation engines can be used to promote new products. For example, when Amazon lists products also purchased in conjunction with a product you just happen to be considering. Neo4j has an HTTP RESTful API that makes it possible for remote clients to connect to it. You can find a number of libraries on NPM which essentially act as wrappers for Neo's RESTful endpoints. Neo Technologies, the company behind Neo4j, has created the now official Neo4j driver for JavaScript. Thanks to NPM, installing the Neo4j driver involves a single command. All right, let's take a look at some code. Here's the Alex.js example from the GitHub repo associated with this presentation. We begin on line 1 by defining the location of the Neo4j database instance. I'm running mine on my laptop, so I specify localhost. The both portion tells Neo that we'd like to use a faster binary connection protocol instead of the HTTP version. On lines 2, we require the Neo4j driver and prepare an auth object to pass to the Neo4j driver setup on line 3. With the driver created, we define an error handler on lines 6 through 8. Next, on line 10, we create a driver session and run a Cypher query on line 12. Note that the run function accepts 2 parameters and returns a JavaScript promise. The first parameter to the run function is a query template, and the second is an object with the query's parameters. This allows Neo to cache query plans for added efficiency. We then use the .then and .catch functions to handle the promise, resolve, and reject cases. Let's take a look at the output. Okay. Yeah, so it basically returns the Alex node. You can see that there. In this next example, we'll run the query where Susan is checking her network for a person with an interest in business. On lines 13 to 15, our query attempts to find a path from Susan to a person with an interest in business. So the query should look familiar here. That person turns out to be Jane. Let's run that. Susan discovers Jane. Using the code patterns we've seen, you'd be able to perform insert, update, and delete operations to build more complex applications. Neo4j is really quite approachable. As we near the end of our exploration into graphs and GraphDBs, I'd like to share a practical example of how graphs are being used in the context of our current political climate here in the United States. No, I'm not referring to the intelligence community, but rather about the power of data in the hands of journalists and citizens armed with technology. On January 15th, 2017, as many of us were resting on a cold and lazy Sunday morning, social news and entertainment media company BuzzFeed posted an article entitled, "Help Us Map TrumpWorld," which compiled a listing of 1,500 people and organizations associated with, in one way or another, Donald Trump's varied business interests. The team at Neo Technologies then loaded the data into Neo4j graph. So the data was originally in a spreadsheet and was imported into Neo4j. Now let's imagine that we're investigative journalists following leads. We jump into our cars for a quick ride over to TrumpWorld. While there, we open up our laptops and begin accessing Neo4j for a 20,000-foot view of TrumpWorld. Let's take a look at this. So first thing I need to do here is actually switch data sets. So I have a small script that will do that for me. This can just take a few seconds. To run that again. Looks like I need a network connection. Darn. Yes, I do. 1 second, folks. Shutterstock, yes, let's do this. Does it have a password? You got it. Here we go. 20. I'm sorry. What was that? After. All right. How about guest? Oh, without the, here, this way. This? Got it. Okay. Does that look right? Hate to hit enter. All right. Come on. Good. Thank you. Okay. Let's load up that data set. Yep, this looks good. Okay, here we go. So now we see that 2,835 nodes were returned, but we're only seeing 300 of them. The interface does this in order to ensure that the visualizations stay manageable. So I'll just go ahead and zoom this a bit. Yeah, you get a sense of the data set size. Let's see. So the orange node in the center is, you guessed it, Mr. Trump. let's see. We can write a query to look at banks and their connections to organizations and individuals. So this is actually an interesting one. If you can look at the relationships. For example, you can see here that Donald Trump is involved with Bank of China. So if you click on that, you can see that the relationship is actually a loan, as reported by the New York Times. And that relationship is also connected to 1293 Avenue of the Americas, a property. So we can also see that if we look at individuals, that Trump has a relationship with Elaine Chao. So that relationship actually is the fact that he nominated her for Secretary of Transportation. And Elaine Chao has connections to Bank of America and Citibank. At Citibank, she was a former employee, and with Bank of America, she was a former vice president. So this allows investigative journalists to sort of navigate data and potentially follow leads. It really helps to understand an interconnection of complex data. We have one last query. Yep, up top. That's Markdown. All right. All right. So if we click on these links, we can actually see the relationships, and we looked at that earlier. So if you wonder, like, connection between Donald Trump and Vladimir Putin is not 6 degrees of separation. It's actually a lot closer than that. We can see that by clicking on these, that Donald Trump and Sergey Milan appeared together in a Facebook photo. Putin awarded Sergey Milan a prize in January 15 for developing ties between Russia and American business people. In 2012, Putin awarded Order of Friendship to Rex Tillerson. Donald Trump tapped Rex Tillerson as nominee for Secretary of State. So these sorts of relationships really help people investigating things. Alrighty. So to recap, we begin our journey by learning about network graphs. Along the way, we discovered that graphs are literally everywhere we look. In fact, network graphs could not be closer to our hearts if you consider the network of arteries within our own bodies. We also learned that we actually think in terms of graphs, and that a graph database is a natural tool for representing our data models and their relationships. Finally, we saw the power of using graph databases to better understand current events. Give graph databases a try. You may just discover that they're an ideal tool to tackle the modern challenges in our highly connected world. If you'd like to learn more about Neo4j, visit their website and check out the article that this talk is based on, published by our friends at Rising Stack. You can find out more about me on GitHub and Twitter, and also at cjust.me. Thank you. Yes, sir.
Recently, MongoDB added some features, graph database features. Have you seen that?
So I haven't seen that, but again, when I mentioned that we're seeing an increased interest, right, in the graph database space, we're seeing hybrid applications. Allegro DB. We're looking at other databases that have key value stores, which look really attractive, right? Because if you need a key value store, maybe you need a document store, and you'd like to play around with some relationships, and it seems really enticing to get an all-in-one package, right? I haven't personally tried them. My limited background actually in graphs is with the fact that I've used Neo4j over the years. It's really been the only one that I've looked at, but definitely the space is growing. Interest is growing. Yeah. All right. Thank you.